All right, so we are going to finish talking through our honors pre-calculus section 1.2 part A class notes. We left off in the last video talking through real life examples of continuous and discontinuous functions. And if you don't remember, go back over that video, look at the solutions that I posted in our Google shared drive. But right now we're going to talk about another important characteristic of a function, which is how it is changing as x changes. Is the function increasing, right? As x increases, is f of x increasing? Is the y value increasing? Is it decreasing? As x increases, is f of x decreasing, or is the y decreasing? Or is it straight up constant, a horizontal line? Again, vertical lines, not functions. Horizontal lines, functions. And horizontal lines are constant. So the official definition is a function is increasing on an interval from a to b if for any 2 points in the interval, a positive change in x results in a positive change in y, which is everything I just said. And so function's decreasing on an interval in the same way as, well, no, I'm showing you something I didn't mean to show you. Sorry. This is what I want. A function is decreasing on an interval from a to b if for any 2 points in the interval, a positive change in x results in a negative change in y. And a function is constant on an interval ab if for any 2 points in the interval, a positive change in x results in no change for y, hence the horizontal line. So example 5, determine the intervals where the functions are increasing or decreasing, and I really probably should have also included the words or is constant, because we actually will see that in example A here. Now, for A, f of x is the absolute value of x minus 1 plus the absolute value of x minus 3. I do not expect you right now at this stage in your mathematical career to know how to graph this by hand, to know how to simplify this expression. It comes from, again, the piecewise definition of the absolute value function that if there's time, I'll show you at the end. It's what I actually accidentally flashed on your screen a few seconds ago. So if there's time, we'll go over it. So what I would expect you to do for these right now, and even this one, this cubic, I wouldn't expect you to be able to graph it accurately by hand right now. So what you're going to do is use your graphing calculator. So plug these into your graphing calculator and then use your maximum or minimum or tracing features to find kind of key points. So for instance, f of x being the absolute value of x minus 1 plus the absolute value of x plus 3, right? The values that make these two absolute value pieces equal 0 are negative 3 and 1. And so those are the two values that will actually divide the domain into 3 distinct intervals. So using our calculator, we can see that. Here's 1, 1, 2, here's negative 3. So we can see that from negative infinity to negative 3, my function is decreasing, right? So it's decreasing for x less than negative 3. Notice I didn't say or equal to. And then it's constant from negative 3 to positive 1. Again, I didn't say or equal to. And it's increasing from 1 to infinity. So what is it doing at 1 and what is it doing at negative 3? Well, it's neither increasing nor decreasing nor is constant. These are important points because that's where change is occurring. So what I could say is at 2, right? Right here at 2, f of x, right? So f is increasing at x equals 2 because at 2, just when x is a little less than 2, it's below. And when x is a little more than 2, it's above. So at 2, it's increasing. At negative 2, f of x is constant. At any point on this line, it's decreasing. At any point on this line, it's constant. At any point on this line, it's increasing. But at the particular points, it's neither increasing, decreasing, nor constant. It's a key point. It's a point where change is occurring. Likewise, so to show this algebraically, because if you think about it, it looks like it's just the equation of a line and then a constant line and then another line with a negative slope, horizontal line, and positive slope. In order to show algebraically what this function simplifies to, we need to use the piecewise definition of the absolute value function, which again, I generally don't teach until I teach calculus, but you're my honors pre-cal, so you're going to get to see it. As far as part B, right, that cubic, again, graph it. Here's the graph that we can see right here. And so a graph over these intervals lets you see that f is increasing below -2. So right here at -2, that's a local maximum, right? So -2, right? So f is increasing for anything less than -2. And then here's a local minimum, 1, 2, 3, 4. And f is increasing for all x greater than 4. Between -2 and +4, f is decreasing. So what do we say is happening at -2 here? Is f increasing? No. Is it decreasing? No. Is it constant? No. It's changing. This is where there's a change. And so this is a local max because it's bigger than all of the things right around it. This is a local min because it's lower. The y value is lower than all the y values right around it. But by no means are these the absolute max or the absolute min because this function keeps going, right? You're going to have y values up here that are higher than that. You're going to have y values that are down here that are lower than that. So we're going to talk about absolute max mins later, I think in our next section actually. All right, so how do we determine these intervals of increase and decrease algebraically? That's something we will absolutely study in calculus, and you need to use calculus techniques. Well, you don't need to, but the easiest way is to use calculus techniques to do that. All right, so let's talk a little bit about another property of functions, being bounded. So a function f is bounded below if there's a number L for low, such that f of x is greater than or equal to L for all x in the domain. L is called a lower bound. Parabolas, right? Y equals x squared. That's going to have a lower bound, L equals 0, right? Oh, that's sloppy. Let's make you draw straight through it. So xy. So lower bound. All x values, f of x, all the y values are, right here, are greater than that lower bound. Notice L equals -1 is also a lower bound because all of these y values are bigger than -1. So there's this other thing called the greatest lower bound, which basically is the lower bound that you would think of. So just be aware, there's this thing called the greatest lower bound. That means the biggest thing that is still less than all of your function's y values. A function is bounded above if there's a number u, think upper, such that f of x is less than or equal to u for all x in the domain. So u is an upper bound. If you turn your parabola upside down, y equals -x squared, right? Then your parabola looks like this. And u, again, could be 0. That looks like a mu, not a u, sorry. Let's make that an actual u for upper, right? Everything is less than 0. So this would be the least upper bound because that's an upper bound too, right? U equals 1 is also, not L, well, U equals 1 is also an upper bound. So we want the least number that's still above, upper than the whole function. And then we reserve the word bounded to simply mean, well, there's a limit above and a limit below. I shouldn't say limit, there's a bound above and a bound below. So give an example of a function that's bounded above, check, below, check, and bounded. Well, so again, what I have here, f of x equals x squared plus 1, right? That's my parabola, but shifted up 1. That's got a lower bound of L equals 1. Or again, any number less than 1 is technically a lower bound. G of x equals 4 minus x squared is bounded above because it's my upside down parabola. And it's bounded above by 4 because that's where the vertex is. It's been shifted up. Or again, it's bounded above by any other number higher than 4 because it's all above. Classic functions that are bounded, sine and cosine, right? Sine, if we remember, looks like this, right? It's bounded above by 1 and bounded below by -1, right? So sine is a bounded function. Cosine is a bounded function. All right, so bounded, that's what we've got there. And then I've already introduced you to them. I've already talked about them. Local mins and local maxes compared to absolute mins and absolute maxes. So a function has a local minimum, f of c. So notice the local minimum is a y value. So it's got a local minimum y value. If that y value is smaller than any other value of f of x in an open interval, so very nearly close to, right, around x equals c. So I'm just going to scroll again right down to this picture. So again, here is my local minimum. That local minimum is negative, what did I say it was? Again, you can trace on your calculator to see. It has a local minimum of -75. So -75 is that y value. So -75 y equals, that's the local minimum value because that y value is less than any y values you're going to get in this small little called neighborhood interval around this x value, which was 4, right? So this point 4 comma -75, the local min is the value -75. That's the local min value, and it occurs at 4. Now again, if you were to continue drawing this graph out, it keeps going. So there's definitely y values that are less than 75, but not around 4. That's what we mean when we're talking about that small interval. All right, so that's a local minimum. If f of c is smaller than any value of f of x, then f of c is an absolute minimum of f. So where do we see absolute minimums? Well, we see them in our parabolas, right? This is the vertex of your parabola. If it opens up, the vertex is where you will always have an absolute minimum because there's no y values that are any smaller than where your vertex of a parabola is if it's opening up. Similarly, so this would be both a local min and an absolute min, right? We also have local maximums, right? A local maximum. A function has a local maximum, a y value f of c, if f of c is larger than any value f of x in an open interval very near and around x equals c. So again, looking at this example we've got right here, let me scoot my picture over so I can scroll better. Looking at this picture, right, this cubic function has a local maximum of 33, right up here, 33, at x equals -2. So -2, 33. This is my local maximum, and the local maximum value is 33. It's bigger than all of the other values on all of the other y values immediately near it in a little open interval neighborhood. But again, it's definitely not the absolute max because it keeps going. So in this example, it has no absolute extrema. Extrema is extremes. No absolute max, no absolute min. It only has a local max and a local min. And again, to find these local mins, local maxes algebraically is what we're going to be learning in calculus. So in the last 10 seconds, again, go look at the solutions for fun if you want to see how to algebraically figure this out.